Okay, in this short program, what we're going to do is we're going to take a look at some of the types of questions you might see on molecular and empirical formulas in Regents format. So what I did here on this side of the page is I brought up some questions from our test bank, the kind of test bank that I would use for your exams or your quizzes, and I have 7 of them pulled up here. So let's go through some of them. It says, given the formula for a compound. This is a structural formula. Let's see, I gotta pull up a pen here. That's from the last program. Let's get rid of that. Okay, so this is a structural formula. It's actually showing you the structure, and it's asking you which molecular formula and empirical formula represent this compound. Well, let's take a look at the molecular formula first. And you'll recall that molecular formula means it tells us the exact number of carbons, hydrogens, oxygens, and in this case nitrogens, because there's some nitrogens in there, for our compound. So we need to write a molecular formula. So let's start with carbon. See, there's carbons here, there's a carbon here, there's a carbon here, there's a carbon here, there's a carbon here. So we've got carbon, and there's 4 of them. I'm going to put little X's on them. 1, 2, 3, 4 carbons. So in this molecular formula, I have 4 carbons. I also see that there's some oxygens here and some hydrogens, so let's do oxygen next. Even though it might not be the same order as what we have down here, we'll deal with that later. We've got 1, 2, 3, 4 oxygens as well. Okay, so let's X them out because we did that already. And then let's look at the nitrogens. We've got 2 nitrogens, 1 here and 1 here. So that's right, we have 2 nitrogens. And then we have 2 hydrogens, 1 here and 1 here. And the reason that I'm crossing them out is so that I don't get anything confused when I'm trying to answer this question. So the molecular formula tells me I have 4 carbons, I have 4 oxygens, I have 2 nitrogens, and 2 hydrogens. Because if you recall, molecular formula tells us exactly the number of atoms that we have in a molecule. So now let's go down to our answers. And in our answer choices, we are looking for one that says 4 carbons, 4 oxygens, not necessarily in this order, but it has to have that number. So right off the bat, this one right here says 2 carbons, and this one says 1 carbon, so we're going to cross this out. And this one again, 2 carbons, 2 carbons, so we can cross that out. Now this one says 4 carbons. That's good, we have 4 carbons here. This one only has 1 carbon, but I'm not going to cross it out because I'm looking for the molecular formula. This might be my empirical over here. So let's just take this 4 carbons, and let's take this one that has 4 carbons. This one has 2 carbons, but this one has 4 carbons, and let's keep these 2 for now. Let's move on to the oxygens. Oxygens, there should be 4 of them. Here I have 4 oxygens. I only have 1 there, but I'm going to still keep it because I still have 4 carbons and 4 oxygens. And this one has 4 carbons and 4 oxygens. So we're narrowing things down, but not very quickly here. Alright, we've got nitrogens, we've got 2 of them. 2 nitrogens, and 2 hydrogens and 2 hydrogens. So these right here are my molecular formulas. These are the same. Ooh, look at that, I drew on it. Okay, so let's get rid of that. Now let's look for the empirical formula. And an empirical formula says that I have the lowest whole number ratio. So if you recall from writing empirical formulas from percent composition, the easiest way to do this was to actually take the lowest number and divide through. Well, the lowest number I have here is 2. So if I take this and I divide all of them by 2, I will get C2, O2, nitrogen 1, hydrogen 1. I only wrote the ones in there so that you can see them visually on the video here. When we do that, we have to see which one of these 2 will match my empirical formula, which has a ratio of 2 to 2 to 1 to 1. Well, this guy has 1, 1, 1, 1. So he is not my answer. And that leaves us with this guy as our empirical formula, and this guy as our molecular formula. So our answer choice is D. Okay? Does that make that question a little bit clearer? Alright, let's move on to question number 2. I'm not going to erase that. I think I have enough room for now. Alright, question number 2. Oops. Given two formulas representing the same compound, formula A, CH3, and formula B, C2H6. Oops, get that. CH3 and C2H6. Oh, my pen didn't. It gets mad at me, this pen, every once in a while, and then it'll yell at me. Alright, we'll read it while this thing resets itself. Given two formulas representing the same compound, which statement describes these formulas? Okay, give me a second here. I got two mice. I got my pen and I got my mouse. Okay, which statement describes these formulas? Formula A and B are both empirical. Well, we know that this one right here is empirical because the ratio is 1 to 3. And that's as low as we can possibly get it. This one, C2H6, 2 is to 6, can be reduced. So this is not an empirical formula, it is a molecular formula. So formulas A and B are both empirical is wrong. Now let's look at choice B. Formulas A and B are both molecular. That is, I can argue that. I can argue that question, okay? Because this is a molecular formula, and this is a molecular formula. Remember, molecular formulas and empirical formulas can also be classified as molecular. It's probably not what they're going for, but let's keep reading. Formula A is empirical, and formula B is molecular. That is true. Okay, so I like choice B and C, but C is a better answer. And then formula A is molecular, and formula B is empirical. Well, formula A is molecular, that's true, but formula B is not empirical because you can reduce this 2 to 6. So this answer is incorrect. Now this question could be challenged. Okay, so let's move on. Number 3. What is the oh, by the way, C is the better answer, and if it was a Regents question, C would be the answer. Okay, what is the empirical formula of a compound that has a carbon to hydrogen ratio of 2 to 6? So carbon is 2, hydrogen is 6. I didn't even read the answer choices yet, but I want an empirical formula where the ratio is 2 to 6. Well, 2 is to 6 is the same as 1 is to 3. And again, if you can't see that, the easiest way to do it is to divide by the lowest number, which happens to be 2. 2 divided by 2 is 1. 6 divided by 2 is 3. So the ratio would be C1H3. If this was the molecular formula, this would be the empirical formula. So now let's go back to our answer choices over here, and let's see if we can find one that says CH3. And there it is. Okay, so now again, look at this question. This kind of contradicts this question right here. I got arrows all over the place here, folks. Let's see if we can erase some of this stuff. Okay, if you need to go back to it, then just go back to it. We got a whole bunch of stuff to erase. You know what? Why am I doing that? Okay, all erased. Good to go. GTG. Let's make it blue, and let's make my pen size really small. Come on, you. Really? You're gonna give me a hard time. Okay. Which formula is both molecular and empirical? Well, let's look at this one right here. Okay? This has a ratio of 6 to 12 to 6. 6 to 12 to 6 can be reduced to 1 to 2 to 1. Can't see my dots there. Okay? So this is molecular. If it was empirical, it would look like this, 1 to 2 to 1. C3H8O cannot be reduced any further because there's a 1 here, and we can't make it any smaller than that 1. So this is an empirical formula. Is it also a molecular formula? Yes, it is. It's molecular because empirical formulas are also molecular formulas. And that's kind of where this question went wrong. Okay? And then we have question answer choice B here, C2H4O2. this is a molecular formula because I can reduce it to C1H2O. Okay, I can make this a 1 to 2 to 1 ratio. And then this one is a molecular formula because, again, I can reduce this to C1H2. Okay, number 5. The formula H2O2 is an example of, well, these subscripts can be reduced, and if the subscripts can be reduced, it is a molecular formula. So it looks like answer choice A would be a good choice. It can't be an empirical formula because empirical formulas mean they have lowest whole number ratio, and these are not lowest whole number ratio. I can reduce them to 1 to 1. An ionic formula. Ionic formulas mean that is a metal and a nonmetal. It's a salt. We don't have a metal and a nonmetal here. Hydrogen is a nonmetal and oxygen is a nonmetal. An organic formula indicates that it contains carbons and hydrogens. And we do not have an organic formula here. There's a whole unit on organic chemistry. If you're watching this at the end of the year for review, then you have already done it. If you haven't gotten to the organic unit yet, we'll get there. Okay, number 6. A compound whose empirical formula is NO2. Let's write it over here. NO2. Could have a molecular mass of. Okay, here's the key word. Could have a molecular mass. Okay, they gave us the empirical formula. And from the last couple videos, you'll recall that empirical formulas are the lowest. So let's figure out what the empirical mass of this NO2 is. N, you have one of them, and it weighs 14 grams per mole. So that gives us a total of 14 grams per mole. My pen's going slow. I'm terrified that it's going to die on me again. Okay, oxygen, you've got 2 of them at 16.0 grams per mole. So that gives us a total of 32 grams per mole. So 14 plus 32, 4 plus 2 is 6, 3 plus 1 is 4, is 46 grams per mole. Well, if NO2 weighs 46 grams per mole, we need to find a multiple of 46, because remember this is times 1. Let me erase this. NO2 times 1 is 46 grams per mole. If it was times 2, it would be N2O4. I didn't leave myself much room here. N2O4. Let's do a better job at writing that down for you. Times 2 would be N2O4. Remember, I'm multiplying everything in the NO2 by 2. So instead of 1 N, I now have 2 N's. Instead of 2 O's, I have 4 O's. And if everything gets multiplied by 2, then the molar mass also gets multiplied by 2. So instead of 46, we have 92 grams per mole. Is that what we're looking for? Oh, look at that. 92 grams per mole. It has to be a multiple. So if it was times 3, it would be N3O6, and then it would be 138 grams per mole. Gives a multiple. And I can keep going up 46, 92, 138, and then add another 46 to that. But you can see that my numbers don't get that high. So this has to be my answer. They could have also asked us to find the molecular formula for a compound of NO2 with a molar mass of 92, and in that case we would have given N2O4 as our answer, because this is the molecular formula that has a molar mass of 92 grams per mole. Okay, now last question on this little guided practice that we have going here. It says a compound contains nitrogen and oxygen in the mole ratio of 1 to 1. Nitrogen 1, oxygen 1. Remember, these subscripts are mole ratio. The molecular mass of this compound could be, well, nitrogen, there's one of them, and it weighs 14 grams per mole. I left the units out there. 14 grams per mole. There you go. And oxygen is one of them at 16.0 grams per mole. And you got 16 grams per mole. So 14 plus 16 is 30 grams per mole. So it has to be a multiple of 30. It could be times 1, which would give you 30. It could be times 2, which would be 60, or times 3, which would be 90, or times 4, which would be 120. So let's look at our answers over here. 14 is not a multiple of 30. 16 is not a multiple of 30. 30 looks like our answer. And 40 is not a multiple of 30. So when we're looking for molecular mass of a compound, and they gave us the empirical by giving us the mole ratio, 1 to 1, we have to have a multiple of that empirical formula. Alright, I hope this little video helped. I'll put up another one in a little while. Okay, let's take a look at our second guided practice. And in this guided practice, I put up a bunch of percent composition questions, including questions on the lab with the copper sulfate pentahydrate that you did during class. And that lab is extremely important, and we'll get to some of those questions as we go on through these guided practice questions. So let's start with the first one, and the first one says, what is the percent composition by mass? So here's our question word, which I'm kind of trying to drive home that you need to be looking for your question word. And in this case, our question word is what is the percent composition by mass? What is the word we're looking for? Percent composition by mass. And when you look at the percent composition by mass, I want you to take a look at your reference tables, and you'll see percent composition by mass. There's a formula for it right here on table T. Okay? So you have to know how to read your reference tables, and when you know how to read your reference tables, things become a little bit easier. So let's take a look at what they're asking. Percent composition by mass of sulfur in the compound MgSO4. Okay, I'm going to come over here, and I'm going to write MgSO4, and I want the percent of sulfur. So that's the part that we're looking for. And if you go back to your reference tables, the mass of the part is going to be the mass of the sulfur. And we need to figure out what the mass of the whole thing is. When you were learning how to do gram formula mass, it was very important that when you did it, that you wrote it in a chart form. And when you write it in a chart form and you calculate your gram formula mass for MgSO4 or magnesium sulfate, you see that the information is readily available to you. So let's go ahead and calculate the gram formula mass, GFM, for this thing. That's going to give us the mass of the whole. Okay, so we have 1 magnesium, and magnesium weighs 24.3 grams per mole. Okay. If you don't believe me, take a look at your periodic table. Magnesium is over here, 24.3. Okay, and get the pen back out. So when we multiply that out, we have 24.3 grams per mole. Sulfur, you have 1 of them, and it weighs 32.1. I again got that. I got that from my periodic table down here. My pen just froze again, so let's just give it a second to reboot itself. It definitely doesn't like me sometimes. Okay, we're getting all of your masses from your periodic table. You have to have your periodic table out on the desk so that you can look these things up. And there it is. It came back from where we left. Okay, let's get rid of that. Okay, green. We have 1 sulfur, and it weighed 32.1 grams per mole. And we had 4 oxygens at 16.0 grams per mole. So 24.3 and 32.1. I can write grams per mole in here. Just trying not to use my pen so much. And 4 times 16 is 64.0 grams per mole. okay? And then you're going to get a total. So we add all these up. 3 plus 1 is 4. 3 plus 1 plus 0. And then I'm going to put my decimal so it doesn't get lost. 4 plus 4 is 8, plus 2 more is 10. Carry my 1 up. 6 plus 3 plus 1, so 6 plus 4 is 10, plus 2 more is 12. And we get 120.4 grams per mole. Okay, this right here is the mass of my whole. That's this. Okay, I'm looking for the percent of sulfur. I'm looking for the percent of this. And so if you follow across your line, this is the part that we are looking for. And the part is 32.1 grams per mole. So the mass of your part is 32.1. Okay, so let's do it down here. Let's do the math. Percent equals mass of my part, which is 32.1. And now we don't need the units because we're doing percents. So 32.1 divided by 120.4 times 100. And that is going to give us 26.6%. Now, if you don't believe me, throw that into your calculators, and when you throw it into your calculator, make sure that you put this number into your calculator first, hit clear, then hit this number into your calculator first, divided by 120.4 times 100, and you're going to get 26.6%. Now, I'm going to erase this, and I'm going to go back to our questions, and we have 20%, we have 27%, 46%, and 53%. Our number was 26.6%. Okay, well, the closest answer here is 27%. So I'm going to erase this, and then I'll just circle that for you. Okay? All right, let's take a look at the second question. In the second question, we have a sample of a substance containing only magnesium and chlorine was tested in the lab and found to be composed of 74.5% chlorine by mass. The total mass of the sample was 190.2 grams. What is the mass of the magnesium? So we know, let's take a little schematic and draw this for a second. We know that we have a sample. I'll make a cloud, right? And out of this, let's not do a cloud. Let's do a circle because it might be easier for you to see. All right, so we've got this whole sample here. That's 100%. The whole thing is going to represent 100%. And they're telling me that 74, or almost 75% of it, right, 3/4 of it, 75%, is chlorine. So let's take this, and let's make this green part, because chlorine is generally green. So let's take this part, and let's say that that is the chlorine part, 74.5%, or about 75%. If the total mass of the sample is 190.2 grams, what is this? What is the mass of the magnesium? Well, that magnesium, if this is almost 75% or 74.5%, this is about 25%, or 100% minus 74.5%. And that gets you 20, what am I doing? That gets you 25.5%. Sorry about that. So this is 74.5%. This is about 25%, which is 25.5%. And so now you know you have 25.5% of this substance being magnesium. Well, they told us that the whole thing is 190.2 grams. Well, if 25.5% of 190.2 is going to be the magnesium, we can now do the math. 25.5% of 190.2 equals the grams of magnesium. Now, you see this word of, when you see the word of in a math problem, and I know with the new math nowadays, I don't know how they teach it to you, but if you see the word of means to multiply. So we're going to take 25.5 and we're going to change it to a decimal because 25.5% is really the same as 0.255, and we're going to multiply it by 190.2 grams. And when we do that, we are going to end up with 48.5 grams of magnesium. Okay, now look at our answer choices up here. 48.5 grams of magnesium. They could have just as easily asked us to calculate the number of grams of chlorine. And if they did that, we would take 74.5% of the 190.2 and we would end up with 141.7. So 74.5% of the 190.2 equals, and then it would be the same as 0.745 times 190.2, and you would get 141.7, and that would be grams of chlorine. Now this number and this number, that is the almost 25%, so that is this section of the pie, and the 141.7 is this section of the pie. It's almost 3/4 of the pie. So when these two numbers add up, we should end up with 190.2, which is what we do. We do end up with 190.2. Okay, let's move on to the next question. So this one was here, and this one was here. Okay, in which compound is the percent by mass of oxygen the greatest? Now, this one is a lot of math going on here. But if we look at the percent by mass of oxygen, let's say we are looking at the reference tables again, because we want percent by mass. Where are my reference tables? We're going to use this formula right here. Percent composition by mass. And we're going to do that for all four of these. We're going to do it for BeO. We're going to do it for MgO. We're going to do it for CaO. And we're going to do it for SRO. Okay, beryllium oxide, magnesium oxide, calcium oxide, and strontium oxide. And I wrote them up here so that I can keep this reference table open for us. Okay, we have to find the gram formula mass for Be and O. Be, pen please, Be has a mass of 9 grams per mole. For space sake, I'm not going to write the units in right now. We have oxygen, which is 16 grams per mole, and 9 plus 16 is 25 grams per mole. Okay, 25 grams. It just kills me not to write those units in. Okay, if I want the percent of oxygen, it's the mass of the part. Okay, the part is the oxygen part, so that's 16. 16 divided by the mass of the whole thing, which is going to be 25, and these are grams, and I'm going to multiply it by 100. So 16 divided by 25 is going to be 64%. Alright, let's do the next one. Change colors just to keep it from getting all squished up inside. Alright, magnesium. And magnesium has a mass of 24. And oxygen didn't change its mass. It's still 16. So 24 plus 16 is 40. And the part we're looking for is still 16. You can see that it is not going to be as big because the bottom number, the denominator, is much larger in this case. So 16 divided by 40 times 100, and we end up with 40% oxygen. Okay, let's do calcium. Calcium has, let's write it down, 40.1 as its mass. Oxygen still 16, so this is 56.1. 16 divided by 56.1 times 100. Again, my denominator is getting bigger and bigger, so my percentage is going to be getting smaller and smaller, and that's 28.5% oxygen. Alright, last one. Strontium, that's a heavy guy. Strontium, because he's getting further down in the group. Right? We've been going down the same group. If you take a look at the periodic table, beryllium, magnesium, calcium, and then strontium, we're going down the group. My masses are getting heavier. Let's get that out of the way. What color didn't I use yet? Let's see. I didn't use blue. Okay, strontium has a mass of 87.6. And oxygen, again, is 16. So 6 plus 6 is 12 plus 1 more is 13, 8, 9, 10, 103.6 grams. 16 divided by what the whole thing weighs was 103.6. And then we get a percentage of oxygen, which is 15.4%. Now, doing all of this here, I have forgotten what the question is actually asking, so we're going to go back to the question. And the question says, in which compound is the percent by mass of oxygen the greatest? Okay, so that's important to know because I didn't know if they were asking for the greatest or the least. And let me point out, another thing that I should point out, when you're doing these kinds of questions, the extreme question, like this is an extreme question, because you see how it says the word greatest, like greatest or least or most or least or biggest or smallest. If it has a extreme question, like has a word that's extreme, then the answer has to be extreme. Okay, it cannot be these two in the middle here because they're not extreme. It's either going to be this one or this one. And because they said greatest, I want the greatest percent, I'm going to go with BeO. So my answer would be BeO. Okay, I'm going to stop because I'm up to 16 minutes in this short video, and I'm going to make it 2 parts, but I'll be right back. And in this question, we have, right here, we're talking about a hydrate, which is a water molecule that has attached itself to a crystal. And this question right here relates itself to the lab that we did in class with the copper 2 sulfate pentahydrate. So it's the same basic idea, and they tend to ask this question a lot on the Regents exam. It shows other. So what we're going to do is I'll spend a few minutes, there's a couple of them here on this guided practice, and we'll see how we can do these questions. Alright, let's read it first. It says a hydrate, which is the compound that includes water molecules within its crystal structure. And during an experiment to determine the percent by mass of water in a hydrated crystal, a student found the mass of the hydrated crystal to be 4.1 grams. After heating to a constant mass, the mass was 3.7 grams. What is the percent by mass of water in this crystal? Alright, let's draw this out so that we can actually see what's going on. And that will be very helpful if you have some scrap paper to draw these things out. Let's assume that we have a hydrated crystal. So here's our hydrated crystal. I always like to draw little clouds, right? And that means there's water molecules that are attached to this hydrated crystal. There's a water molecule, here's another water molecule, there's another water molecule. I have no idea how many there are in there, but you get the idea. So you've got this crystal, and it has water molecules that are attached to it. And this whole Megillah right here, that whole thing weighs 4.1 grams. That's what it says. In the hydrated crystal, a student found the mass of the hydrated crystal to be 4.1 grams. Think about that for a second. You have a sponge, and in that sponge you have these water molecules. And if I weigh the sponge and the water molecules, the sponge is hydrated, that whole thing weighs 4.1 grams. Then we're going to heat this sucker up. We're going to take it, and we're going to put some fire under it. Let's draw some fire. Okay, so there's some fire, and when we heat that up, what happens to the water molecules? Well, the water molecules decide it's too hot, and they go away. And they're here. Whoa, Nelly. They really wanted to escape. Okay, so we got some water molecules. They're not attached anymore. And my pen just died, so bear with us, because you know you've seen this before in other videos. My pen dies. Well, those water molecules, they escape. And when they escape, they're no longer attached to this crystal. So we can reweigh that crystal, and when we reweigh that crystal, let's see if we can get this to work. When we reweigh that crystal, come on, you can do it, pen. Okay, so they're really gone, so they're going to make me do it all over again. When we reweigh the crystal, let's see. The crystal is going to weigh less than when we started, because those water molecules are now up here in the atmosphere. So this is just the crystal. Okay? Before, we had the crystal with all the water molecules attached to it, and it weighed 4.1 grams. Well, now, after we heat it to a constant mass, we'll talk about that in a second, we've got the crystal weighing 3.7 grams. So if the crystal weighs 3.7 grams, and it used to weigh 4.1 grams, and it now weighs 3.7 grams. If we take the difference between those two numbers, which happens to be 0.4 grams, that 0.4 grams indicates the mass that was lost when the water left. So the water must have weighed 0.4 grams. Because if we started with 4.1 and the only thing we have left is 3.7, then the water must have been 0.4. Okay, so let's just write what we know. We know that the hydrated crystal, that's the crystal with the water on it, weighed 4.1 grams. We know that the anhydrate, that's the crystal without the water, that means the water left, and means without water, weighed 3.7 grams. Let's keep our units on there. So when we subtracted those guys, we got 0.4 grams of water. The water weighed 0.4 grams. Now we want to figure out the percent of water that was lost, the percent by mass of water in this crystal. Well, we have everything that we need to do this, because we know that, the reference table is here, we know that our formula for percent of water, let's go down here, percent composition by mass, right here, is the mass of the part, and we have that, the part which is the water, over the mass of the whole thing. Well, this is the whole thing, because this was the water and the crystal. This was the crystal without the water. Just to make things clear, this was the water and the crystal. The hydrate means water, and this was just the crystal. Okay, so the whole thing was the water and the crystal was 4.1. So if we're going to find percent, we have percent equals mass of part over mass of whole. Sometimes the pen writes better than others, doesn't it? Okay. Times 100. And the part was 0.4, because that's the water, right? We want the mass of the water. That's the part we're looking for. And the mass of the whole thing was 4.1, okay, times 100. 4.1, 0.4 divided by 4.1 times 100. Plug it into your calculator, and you're going to get 10.8% water. Okay, let's go back to our question. That's not it. Hopefully it's here. Okay, a hydrate, this is the question we were working on. We got 10.8% water, which is close to 11%, which is right here. Okay, I'm going to stop this and see if I can get my pen to work a little bit better, and we'll continue on here. And question number 5 is based on the copper 2 sulfate pentahydrate lab that you did in class, except for on the Regents exam we don't have a lab practical. So what they'll do is they will give you the lab information in a chart form, and you see that for question number 5 right here, and you're also going to see that on question number 7, and they're eerily similar to each other. And you actually saw it for question number 4 as well, except for they didn't give it to you in chart form. So let's take a look at question 5, and I'm going to attempt with my great artistic skills to draw this for you so that you can get a visual idea of how they are giving you the information. Alright, in this one it says the mass of the crucible. So we've got a crucible here, and a crucible is just a bowl. You used it in lab. It is a ceramic bowl. And inside that crucible you have hydrated crystals. Now the word hydrate means that the water molecules are attached to it. And in your lab, those crystals were blue. So let's put that in here. Okay, and they have water molecules attached to them. I'm just going to put 2 on there to show you that those water molecules are attached. And this whole Megillah right here, the crucible and the hydrate with the water molecules attached to it, weighs 7.5 grams. Okay? And then they tell you in the next line right here, mass of the crucible, the bowl by itself, without anything in it, weighed 6.9 grams. And then they tell you the mass of the crucible and the anhydrous crystals after heating. So let me get my bowl back in black here. And here's my bowl. And after you heated those crystals turned gray. Now I don't have gray. Oh yeah, maybe I have gray. Here, let's try this. Oh, look at that. Gray. Okay, those crystals turned gray because the water molecules left. They went. Let's put them down here. The water molecules are down here. They evaporated into the atmosphere, those water molecules that were attached. So right now I have the bowl and the anhydrous crystal, and they told us that that thing weighed 7.2 grams. Okay, we want to figure out what the, here's my question word, what is the percent by mass of water in the hydrate? So the percent by mass of water is a formula that's given to you on the back of your reference tables right here, percent composition by mass. And to figure out that percent composition by mass, we need the mass of the part, and we have to divide it by the mass of the whole. Now the part that we're looking for is the water, the percent by mass of water. That's the part. So we have to figure out how much of this is the water. Well, to do that, we have a couple options, but the easiest way that I see it is to take the mass of the crucible, the mass of the hydrated salt, that's the salt with the water molecules attached to it, and if we subtract the mass of the crucible and the anhydrous salt, because the water molecules are now over here, we're going to get the mass of the water. So if we take 7.5 and we subtract 7.2, I'm going to find out how much these water molecules weighed. Because the only thing that's not in here, in this crucible, is the water. I hope you understand that. So we're at 7.5 minus 7.2, and we're going to end up with 0.3. So let me get my pen back. Okay, so these water molecules are going to weigh 0.3 grams. Okay, that takes care of the mass of my part. Now, but how much did the whole thing weigh? Well, when they talk about whole thing, they're not talking about the mass of the bowl. Nobody cares about the mass of the bowl. The bowl is just there to hold the stuff. So when we talk about the mass of the whole, we're talking about this hydrated crystal, the crystal with the water molecules attached to it. And in order to figure out how much that crystal with the water molecules attached to it weighed, we have to subtract the mass of the bowl. That's why they gave us the mass of this empty bowl. So we have 7.5 minus 6.9 is going to give me the mass of just this blue thing in here, this blue crystal with the 2 water molecules attached. So that, the hydrate, let me write that over here, the hydrate, which is this, just that, come here you, with the 2 water molecules attached to it, is going to weigh 7.5 minus 6.9, which is 0.6 grams. So here's my part, Here's my hole. Now I gotta stick it into the formula. Okay, I'm gonna clear all this. If you need to, go back in the video and look at the picture again. So when I pull up my formula, I'm gonna have the water, which is the part. So my percent is going to be the mass of my part, which is going to be 0.3 grams, and the mass of my whole, which is 0.6 grams, and I'm going to multiply it by 100, and I'm going to end up with percent is going to equal 50% water. And I can write water in here so that everybody is all happy. Okay, so here's my answer right here, 50% water. Okay, now let's move on to question number 6. In question number 6, it says the percent by mass of carbon in HC2H3O2. And just for fun, I'm going to write it over here. I already wrote it wrong, so let's do HC2H3O2. Okay? I want the percent by mass of carbon. So to get the percent by mass of carbon, I have to figure out what this whole thing weighs. I also have to figure out what the mass of the carbon weighs. So let's start with the whole thing. We've got H. Now we have 4 H's. We have 1 H here, and we have 3 H's here. So there's a total of 4 H's, and they each weigh 1 gram per mole apiece. And I am going to have that weigh a total of 4 grams per mole. Now, carbon, there's 2 of them. They weigh 12.0 grams per mole apiece. That gives me a total of 24 grams per mole. Oxygen, there's 2 of them. See, because of the subscript of 2, times 16.0 grams per mole. And that's going to equal a total of 32 grams per mole. When I add all of this up, 4 plus 4 is 8, plus 2 more is 10, 3 plus 2 plus the 1 that I carried over is 60. Sorry about that. Come back here. Okay, we have 60 grams per mole. That's the total. 32 plus 24 plus 4. So my total mass is 60. And my part is 30. Why do I keep saying 30? I have 30 on the brain for some reason. 24 grams per mole. So my part is 24 grams per mole. And my whole is 60 grams per mole. And we're going to multiply that by 100. And when we do 24 over 60 times 100, we are going to get 40%. Now, the question answer choices do not give me a choice of 40%. But because I wrote all of this out, this is the answer. 24 divided by 60 times 100. Okay? Alright, now let's do the last question on here. Oops, I gotta erase this. Okay. A student obtained the following data to determine the percent by mass of water in a hydrate. This question is identical to the previous question, number 5, except for you have different numbers. They give you an empty crucible, which is your bowl, and it has a cover on it, which I'm not going to even attempt to draw. And they're telling you that that thing weighs 11.70 grams. And then they say there's a mass of the crucible and the cover, and the hydrated salt before you heat it. So there's your bowl again, and inside the bowl you have that hydrated salt, which means it has the waters attached to it. I'll put them on there for you so you can visualize it. And that weighs 14.90 grams. Okay, so right now, using these two drawings, I can see that mass of this blue thing with the water molecules attached, which is my hydrated crystal, is going to weigh 14.9 minus 11.7. So let's figure that out. Let's do 14.9 minus 11.7. Where should I write it? 14.9 grams minus 11.7 grams, and we get 3.2 grams of the hydrate. That's the one with the water molecules attached. Now I'm going to have heated it, and after I heated it, the hydrate is going to turn gray because the water molecules are no longer there. They left. They went on vacation. And that weighed 14.53 grams. Okay? 14.53 grams means that the water is gone. So the difference between this and this, where there is water and where there isn't water, is going to give me the mass of my water that left. So we can do 14.9 minus 14.53. .37 grams of water. Now you could have done it another way. You could have actually figured out the mass of the anhydrate by subtracting 14.53 minus 11.7, and then you would have the mass of the anhydrate, you would have the mass of the hydrate, and then if you subtracted those, you would get the mass of the water. Okay, so we've got the mass of our water, we've got the mass of our hydrate, and we need to find the percent composition of water. So we have the mass of our part, which is right here. Let's get the mass of our part. This is the mass of my part. This is the mass of my whole. And I am going to divide them. So I'm going to take 0.37 grams of water. Oh no. Why does the pen always fail me when I'm just getting close to it? Okay, hold on. Let's get this rebooted. Don't panic yet. I'll let you know when to panic. Okay, reopen. Let's see what it gives us. Ooh, almost the whole thing. Okay, so we've got 0.37. It always makes my pen go. 0.37, which is the grams of my water. It's a water. And it's going to be over 3.2 grams of the whole thing, which is the hydrate. Oh, same spot. I did it again. Okay, let's not write it down there. Let's write it up here and see if this works. 0.37 grams of my water over 3.2 grams of my hydrate times 100. I did it again. Okay, well, I'm going to attempt to just tell you the answer, because obviously it does not want to finish this question. Let's see. 0.37 grams of water over 3.2 grams of hydrate times 100, and we're going to get 11.6% water. Okay? So try that on your own, see if you can get those, and when you get 11.6%, you can look over here and it's approximately 12% on the answers. Alright, I'm going to see if I can get this working again, and we'll try with the next program.